We're Group 6B, and this is our BME 111 final project on blood bag and tubing. So blood bags are used as a mechanism to collect, separate, store, and transport blood and blood components. The conditions of the bag are meant for the administration and preservation of blood. Along with the blood bags, thin tubings are designed to collect and transport blood from the source to the bag. Two common materials found in blood bags and tubings that we will be going over are polyvinyl chloride, or PVC, with diethylhexylphthalate plasticizers, or DEHP, and ethylene vinyl acetate, or EVA. The monomer of PVC is vinyl chloride, which consists of a carbon-carbon double bond that forms the backbone of the polymer. The carbons in the monomer are covalently bonded to 3 hydrogens and 1 chlorine, which is the side chain. The polymer is formed by free radical polymerization, which causes a break in the double bond and allows for chain growth polymerization. The DEHP plasticizer is composed of a diester of phthalic acid and the branched chain 2-ethylhexanol. When added with PVC, the phthalic acid part of DEHP undergoes hydrogen bonding with the attached hydrogens in the polymer. EVA is a copolymer that is formed by 2 subunits of ethylene and vinyl acetate monomers. The ethylene monomer is a complete hydrocarbon, while the vinyl acetate monomer consists of a vinyl group which is chemically the same structure as ethylene with 1 less hydrogen, thus providing one of the carbons with a spare valence electron. This electron is covalently bonded with acetate, which serves as vinyl acetate's functional group. The EVA polymer is polymerized through free radical polymerization, by which both monomers are covalently bonded to one another or themselves. The physical structure of PVC is primarily a linear polymer. Generally, rigid, unplasticized PVCs are found to be about 5 to 10% crystalline, which makes PVC intrinsically an amorphous polymer. The random organization and arrangement of chlorine atoms on the polymer indicate that most polymerized PVCs are atactic. However, there is some degree, about 30%, of symbioticity that contributes to its small percent crystallinity. PVC's physical structure also provides it with a melting temperature between 170 and 210 degrees Celsius, and a glass transition temperature between -50 and -5 degrees Celsius. However, the addition of DEHP plasticizers weakens the intermolecular forces and increases the intermolecular distances between the polymer segments in order to alter the arrangement and rigidity found naturally in unplasticized PVC. When a DEHP plasticizer is added, the conformation change of the polymer's physical structure leads to increased flexibility in regards to lower crystallinity and higher temperature effects, all properties that are preferably needed for blood bags and tubes. Typically, blood bags are found to be comprised of 40% DEHP and 55% of PVC by molecular weight.
However, the effects of plasticizers are not fully understood, besides the fact that the more compatible the plasticizer is,
the less crystalline the polymer would be. EVA is physically structured as a linearly random copolymer with an arrangement of ethylene and varying amounts of vinyl acetate, or VA, distributed across the copolymer depending on the desired properties of the manufacturers. Typically in blood bags and tubings, EVA is found to have a 15 to 45 weight percent range of VA with an increasing amount of VA content leading to decreasing crystallinity and increased flexibility. Furthermore, when EVA is found to have a higher VA weight percent, the copolymer is generally considered to be increasingly amorphous. EVA's melting temperature is found to be between 40 and 110 degrees Celsius, with increased VA content contributing to lower temperatures. The glass transition temperatures of EVA was found to range from -25 to 0 degrees Celsius, respectively.
Figure 10 will just be focusing on the stress-strain curve of PVC with DEHP, curve B. This curve is representative of an elastomer because the presence of DEHP contributes to PVC's amorphous behavior. Sections 1, 2, and 3 of the curves represent plastic deformation, elastic deformation, and failure, respectively. We will focus on both stress-strain curves in Figure 11, even though only EVA 28 is labeled. EVA 18 and EVA 28 mean EVA with 18% and 28% VA weight content, respectively. Although EVA is semi-crystalline, these curves are more representative of an elastomer because of increased VA content. Both EVA curves and the PVC curve have the same shape and corresponding molecular behaviors. These EVA curves may seem steeper, but that is because the scale of stress on the y-axis is different. Stiffness was found to be very similar. This makes sense because both materials should be similar in how their mechanical properties affect their function as a blood bag. EVA can have up to 45% VA weight content, so EVA will generally have a higher ultimate tensile strength. EVA is more ductile and has a higher toughness. Differences in these mechanical properties are not necessarily important because blood bags do not typically experience deforming mechanical forces. Calculations for each mechanical property can be found here. DEHP is not chemically bound to PVC, so DEHP can migrate from PVC bags into the blood. Figure 12 shows that as storage time of blood bags increase, concentration of DEHP in red blood cell units increase. After 14 days, DHP concentration increases greatly. In the theoretical model of a 5 kilogram child, the concentration of DHP found in a red blood cell unit exceeds tolerable daily intake by over threefold after just 1 day. EVA does not have plasticizers, so there is no concern of plasticizers leaching from EVA bags.
Due to the fact that blood bags are not medical devices implanted inside of the body and are not used for long periods of time, degradation mechanics are not applicable and will not be covered in this presentation. Both PVC and EVA are uncharged and hydrophobic, allowing for blood to stick to the inner surface of the blood bags. However, with the coating of heparin on the PVC inner surface, the blood bag can demonstrate reduced adhesion of blood coagulation proteins such as fibrinogen. This reduced blood clotting and thrombogenicity thus increases blood cell viability for patient use. Due to the fact that EVA does not contain a plasticizer, its surface is rougher than that of PVC. This causes EVA to be more abrasive as well as induce more adhesion, which is the reason that its water contact angle is less than that of PVC's. EVA thus has a greater tendency to allow stored blood to cling to its inner surface and form clots than PVC does.
While the DHP-PVC mix has been one of the leading materials used for blood bags and tubing, it has raised biocompatibility concerns because of DHP leaching, especially in the presence of lipids. This matter is highly applicable to the fact that blood components can be stored with albumin, a carrier protein of substances like fatty acids. The negative health risks include carcinogenic effects when degraded to its monoester MEHP, dysfunctional endocrine system, and acidosis-laden kidney failure. DHP is also listed by the US EPA as a pollutant. Although its concentration in this context is below listed exposure limits, the leaching can build up to having considerable effects. On the other hand, EVA lacks phthalates, which is why it has been used alternatively, especially for those in more susceptible states, such as pregnancy. While the biocompatibility of EVA is considered to be more favorable than that of PVC material, EVA has its own set of limitations that prevent it from being used universally. Firstly, EVA has a low melting point, even with high concentrations of EVA, which makes it difficult to undergo necessary high-temperature sterilization. Additionally, the rough EVA surface, as discussed in previous slides, can induce blood clots. Lastly, compared to the DHP additive, EVA is unable to interact with red blood cells in a way that can prolong storage. This is also the main reason why plasticized PVC material is used for all types of blood storage despite the health concerns. While the exact mechanisms of RBC storage are unknown, it has been proposed that DHP causes a shape change of red blood cells that reduces the chances of hemolysis, or RBC rupture. To address these challenges, the additive composition of the current materials will need reform. Best change would be to remove DHP with its proven health risks to a new plasticizer in PVC with reduced leaching. For example, plasticizer known as THTM leaches into blood 100 times less than DHP when mixed with PVC due to its higher molecular weight and increased steric hindrance, which makes it harder to leach through chemical interactions. As a result of this, changing blood pH is not as big of a concern, but the shelf life of blood materials would decrease to around 21 days. Another change could be to the EVA material by including additives that improve its properties. One such additive could be vepaloxamer, which studies have shown have been able to reduce hemolysis significantly and red blood cell coagulation. Here are our references. Thank you so much for watching.